So we have limit as x approaches infinity of, sorry, I rewrote on my answer key so I could tell I changed the question from what I originally had. I wanted to make sure I wrote the right thing down. Sometimes I get lazy and just make adjustments instead of starting over a new key when I change a problem. All right, so here's the problem. If I plug in my infinity right now, you get infinity minus the square root of infinity squared plus 4 times infinity. So essentially infinity minus infinity. We know we can do infinity plus infinity or infinity times infinity. So this isn't helpful. Like problem F, we talked about that one yesterday. We had an infinity time, or infinity minus infinity on that one. So we had to factor, and then we were able to work it. Factoring isn't an option on this one. But what's a strategy that we have used anytime we see radicals? This is over 1, so I'm going to multiply by x plus on top and bottom. So if I do that, so if we multiply x times x is x squared plus x times my radical minus x times my radical cancel, minus the x squared is 4x plus 1 over my denominator. Okay, pretty ugly at the moment. We can simplify on the top if we distribute that negative. Positive and negative x squared cancel. So I have a negative 4x minus 1 over my denominator. Now, if I try to plug in infinities now, I'm getting infinity divided by infinity. And I can't do that either. So, when we're doing a limit as we approach infinity, and we have a fraction, and we're getting infinity over infinity, what was our strategy?
Do the 1 over the highest power.
So we have 1 over x. We do it on top and bottom. Now, if I do that, we get a negative 4 minus 1 over x plus, if I want to take this x under a square root, x is the same thing as the square root of x squared. So under the radical, I'm dividing by x squared. So I get 1 plus 4 over x plus 1 over x squared. Now we can plug in infinity because the number over infinity always turns into 0. So you get negative 4 minus 0 over 1 plus the square root of 1 plus 0 plus 0. So negative 4 over 2 is negative 2. What else? Is that one okay now? You understand? Okay. So let's go to problem 10. So it told me our displacement, so that's how far you've moved, is given by this equation. Part A, find the average velocity. We know average velocity is the same thing as saying slope. Over the interval 1 to 3. What I just gave you there are two different x, or in this case t values. You have to plug them into the equation to get your y, or my s in this case. So if I put in a 1, I get 1 plus 2 plus 1/4, so 3 1/4, or 3.25. I plug in a 3, I get 1 plus 6 plus 9/4, so 9.25. The average velocity says do the slope between them. y2 minus y1 over x2 minus x1. So 6 over 2 is 3. So my slope is 3. Units would be, my y was meters, my x was second. Part B says find the instantaneous when t is equal to 1. Now back when we did instantaneous, that's when we were making those tables. We had to have a t, an s, and then a slope. And we had to do 2 tables. So our times, we are approaching 1, so we do things smaller than 1. And then things bigger than 1. So I'm comparing them all to this point. First I have to plug these things in to get my y. So if I put in a 0.9, we get 3.0025. If I did 0.99, get 3.225. And 0.999, I get 3.2475. Do you guys know where I'm getting those? And I did the slope between each of these ordered pairs and my point 1, 3.25. So y2 minus y1 over x2 minus x1. So this one is 2.475. This one gives me 2.5. This one is also 2.5. So what does it appear this table is approaching? 2.5. But we know it's not enough. We had to check both directions. So then if you plug in a 1.1, can I just tell you what these numbers are? If you put it in, you get 3.5025, 3.275, 3.2525. And then you do your slope. And again, we see these slopes are approaching 2.5. So our instantaneous is 2.5 meters per second. Now, on the test, without a calculator, could I expect you to do this? No. I can basically promise you, you will have a question like part A. Okay, finding an average velocity. It would be a reasonable equation where you could plug in 2 x's, get your y's, and find your slope. For part B, I would probably have to provide the table for you and just say, based off this table, what's the instantaneous velocity? And you have to know that you're just looking at what we approach for that. Okay, so you would not be expected to complete the entire table without a calculator. I'm not quite that mean. So, my expectations are high, but maybe not that high for you to do that much math. All right, 14. We need this function to be continuous. If it's continuous, all of these pieces have to match up when you draw the graph. So what we really need to look at are these breaking points. For instance, if I focus on these first two pieces, those pieces connect when x is 2. So I have to get the same thing when I plug 2 into both of them. Now the first one, can I plug a 2 into that? No. But if we factored, those cancel. So now could you plug a 2 in there? So when x is 2, I need those to match. So it'd be 2 plus 2 has to equal a times x, which is 2. So 4 is equal to 2a, so my a value has to be 2. Does that make sense? So then from there we have a couple different ways of figuring out the next one. So if I just focused on, let's say I did these two for now. When did those pieces have to match up?
3.
When x is 3. Okay, can I plug 3 into both of those?
Yes.
Yes, so let's do that. So when x is 3, so we get 9 minus 3b plus 3 has to equal 6 plus b. That's 12. Okay, so if I subtract my 6 out of my 3b, divide by 4, so b is 3/2. So in order to make these continuous, so that when I graph it the pieces connect, a has to be 2 and b has to equal 3/2. What else on this? Alright, so first we have to graph this function. So when we graphed piecewise functions, we made a t-chart for each piece. So that's where I'm going to begin. Alright, so for the top piece, even though it's only for x is less than 0, you have to plug in the 0, but what kind of circle would it be? Open. And then you need things smaller than 0, so maybe -1 and -2. So if we put in 0, we get 1. If I put in -1, 1 plus 1 is 2. -2, 4 plus 1 is 5. So 0, 1 is open. -1, 2, -2, 5. If you can't tell what it is from now, you could always do more points, but what we're getting is part of a parabola. And it only extends to the left because it's only true for x's less than 0. The middle one, 3 if x equals 0. The only x value that works is 0, and we get out 3, so that's just a single point. And the last one, again, you have to put in 0, but it would be open because it didn't have an equal to, and then x's have to be greater than that, so maybe a 1 and a 2. So if we put in 0, we get -1. If we put in 1, -1 plus 1 minus 1 gives us -1. If we put in a 2, -4 plus 2 minus 1 is -3. Okay, so 0, -1 is open. 1, -1, 2, -3. That looks a little bit weird. If you look at this, we know x squared should look like what? A parabola. If I get the same point twice in a row, what happened in between those two? It already peaked and is coming back down. So it's not just a flat line all the way across, and you could certainly plug in another point if you needed. But what happened is the vertex is somewhere in between there. So we've got to go up, and then we're coming back down. I can't hit my points for some reason here. So it looks something like that. So what's the only place where it's discontinuous? And we could have predicted that from here. The only way it wouldn't be is if it was those pieces connected when you plugged in 0. So we know it's discontinuous at x equals 0. And then I asked you to classify it. So technically, if you're coming in from one side, it's like a removable because this piece could be filled in. But if I'm coming in here and I'm coming in here, do the left and right pieces match up? No, so that makes it a jump discontinuity because the left and right don't match. So you would have to jump from one piece to the next. We need to know the definitions. You should know like the formal definition of a limit. That would probably be like a multiple choice type question. And I've already told you that this test would have a bonus question on it, and what would your bonus question be? The proof. So like problem 12, your epsilon delta, I already told you that would be a bonus question. But you should be able to recognize the actual formal definition of a limit in a multiple choice type question. So I've tried to put all the stuff we need to know together because it gets confusing if I'm asking, average versus instantaneous velocity, the types of discontinuity versus the rules of discontinuity. So I tried to create one page that would summarize everything for you. So let's go through this. Very first thing on here, knowing the difference between average and instantaneous velocity. Average velocity is the slope between two ordered pairs. How do we find slope? Or instantaneous velocity is the value the average velocities approach. That's when we had those tables. So like your x, y, and slope. And whatever your slope approaches, that's your instantaneous velocity. So average velocity, you need two full ordered pairs, find the slope between them. If you have a bunch of average velocities, you can look at what they're approaching to get your instantaneous, the velocity at a particular point in time. All right. Then I have my rules for continuity. So remember continuity, we have a couple different things I might ask. The rules versus the type of discontinuity. Remember for our rules, if any rule is broken, then it's discontinuous there. A lot of times I would give you an equation or a graph and say, where's this discontinuous? And tell me which rule was broken. So the three rules, the function has to exist, the limit has to exist, and they have to be equal to one another. So a situation where the function doesn't exist might be like on a graph. If I just had an open circle. Okay, in this case, f of 2 does not exist. So it's discontinuous when x is 2. What would be a situation where there isn't a limit? Okay, so something like this one's going down, and Okay, the limit doesn't exist there. Another situation might be like if I gave you one and maybe you have a piecewise function, it's got a break in our graph right there. Okay, in the second one I drew, does the function exist when x is 1? Yes, because I have a closed circle. In this first one, does the function exist there? No, so technically the first graph broke both rules. Second one, the function exists, but the limit doesn't. So in both cases, the limit does not exist at x equals 1. Third rule, the function has to equal the limit. So if I want to draw a graph where the function exists and the limit exists, but they're not equal, what if I did something like this? Does my function exist? Yeah. Does my limit exist? Yes. But they're not the same. So the limit does not equal the function at x equals 0. Alright, so if I ask you which rule is broken, it's one of those three. Does the function exist? Does the limit exist? Are those things equal? And you should be able to identify that. Usually if I was asking you to tell which rule was broken, I was giving you a graph to look at. Now, if something isn't continuous, we can classify the different types of discontinuity. And so there were 3 types: infinite, jump, and removable. So infinite, on a graph, what did that look like?
That was insane. Or negative.
Something like spinning, spinning down. What did it look like if you had an equation?
Like x minus 1 over x plus 2.
Something where you had that variable on the bottom and it didn't cancel out. So you should be able to identify it from either the graph or the expression, and it happens at a vertical asymptote every time. So if you get a vertical asymptote, that's your infinite. What does a jump look like in terms of a graph?
There's like 2 separate pieces.
How did you identify it from an equation?
Piecewise.
Yes. So right, so these happen in our piecewise when you have a jump between the pieces. And the third type, removable. What did that look like? Yeah.
On the graph, just like a point.
On a graph, it's like whole. From an equation, it's when something does cancel out. Or it even happened on the piecewise, when one piece is not equal to, and one piece is equal to. Sorry, I kind of ran out of space there. Can you tell what I was trying to say? So if the pieces aren't less than or greater than, but if they're equal and not equal. So it's anytime you have a hole in the graph. So a lot of times we were classifying them without the graph itself. I mean, it could be from a graph, but a lot of times we're just looking at the expressions themselves and deciding, does this have a vertical asymptote? Would those factors cancel? Or do we have a hole in those graphs? Any questions there? All right, so do we understand the difference between our rules of continuity and our types of continuity? Okay. Limits. So, formal definition, I told you this would be a multiple choice and a bonus question. Multiple choice for the definition itself, bonus for a proof. Okay, so if the absolute value of x minus a is less than delta, then the absolute value of fx minus l is less than epsilon. It tells you it is a limit if you can get closer to your limit value by just making your x get closer to the value you're approaching. When we did our definition, we always wrote out the definition first, found our delta, and then did the proof from there. With our limits, if we just are approaching a number, we tried to plug it in. That's fine as long as what doesn't happen. Right. If we have like a domain error, like a 0 in the denominator, that doesn't work. If we can't plug it in, then we tried to factor and reduce, multiply by a conjugate, and sometimes we just had to resort to logic, thinking through those problems. When we are approaching infinity, we're trying to plug it in. A lot of times to get there, we have to divide by the highest power of x, again, multiplying by the conjugate, or sometimes reasoning to get there. So those were our strategies. With our asymptotes, two different kinds of asymptotes. Vertical are x equals anything that makes the denominator 0. So all you have to do is factor the bottom, and those are your vertical asymptotes. Horizontal, you have to do the limit as you approach positive infinity and negative infinity. I told you most of the time those are the same, but in some cases they aren't. Like if you have piecewise functions, things with radicals, it can get a little ugly. So that's why we had to check both. And then horizontal is always y equals a number. Vertical is x equals. So the other thing I noticed is the reasoning problems are sometimes hard. So let's just make sure we know what these things mean. If I say the limit as x approaches infinity of 1 over x, 1 over infinity always goes to 0. What about 1 over negative infinity? 1 over a smaller and smaller positive number. If you need to, think about it. 1 over 0.1 will give you 10. 1 over 0.01 is 1 over 100, so you get 100. 1 divided by 0.001. 1 divided by 1 over 1,000 gives you 1,000. So it's getting bigger and bigger. So that goes to infinity. This is a typo. That should be a negative. 1 over 0 from the left. What happens if you have 1 divided by a smaller and smaller negative number? Negative infinity. What if you have a really big positive number times a really big negative number? What happens if you have a really big number minus 1? Still really big number. What if you have a really big number minus a really big number? Can't do it. So you need another option. A lot of times we tried like factoring or something like that. So we could get to, if we can get a big number plus a big number, we can do it. But we can't do a big number minus a big number. All right. Any questions over that summary sheet? Talk about it. What did you do for the first one? Okay. So if you try to plug it in right now, you're getting 0 on the bottom. So you always factor to see if we get lucky and something cancels out. Unfortunately, it didn't. But we can think about it. We are approaching -3 from the right. So if I put a -3 in the top, -3 plus 1 is negative 2. On the bottom, we have negative 3. Negative 3 plus 3 is 0, but I'm approaching from the right. I'm putting in something bigger than negative 3. So if you take a number bigger than negative 3 and add 3, so like negative 2.9, negative 2.99, we're getting positive answers every time. 2 negatives give us a positive. If you wanted to, you could even think of it as like 2/3 divided by a smaller and smaller positive number. What happens if you take a number and divide by a smaller and smaller number? It's bigger and bigger, so this is going to infinity overall. Alright, this one. Can I plug in 0? No, so what's our strategy? Plus 4 plus 2. So if we do that, multiply those radicals, they cancel, so it gives me x plus 4. Outside and inside cancel, so minus 4 for x times radical x plus 4 plus 2. So my 4's drop on top. Then my x's cancel, so now I can plug in. We get 1 over the square root of 4 plus 2 or 1/4. So anytime we have problems with radicals, try the conjugate. Even like that one that we did that wasn't a fraction. We worked off the study guide. Put it over 1 and multiply by the conjugate. Alright, this third one. Can you just plug in infinity? No, because you get infinity minus infinity. What could you do instead?
Take a x free.
Okay, so infinity squared, a really big number squared is still a really big number. A really big number minus 1 is a really big number. A big number times a big number is a big number. So we're still getting